You're more than welcome to.
Oh, did I think you're muted.
Okay, shall I start?
Yeah, go ahead.
Well, thank everybody for coming to this talk, and thank you for inviting me. It's always a pleasure to be here and to chat with everybody. As we said, feel free to ask questions, interrupt me at any time. So my name is Gabriele. I'm a scientist at the California Institute of Technology, and I'm a member of the LIGO laboratory. So LIGO stands for Laser Interferometer Gravitational Wave Observatory. So we build instruments to study our universe, but the difference is that instead of studying them using light or radio waves, as we have been doing for a long, long time, we finally managed to construct some instruments, some astronomical instruments that allowed us to detect gravitational waves, which is a different kind of signals that arrives to us from the universe. So as you can imagine, every time you open a new window into the universe, you discover a lot of new things. So that's why I would like to spend the next half an hour or so, or a little bit more, we'll see, to try to convince you why it is interesting to study the universe with gravitational waves. So before we do that, I'll have to introduce some of the actors here. So discuss why, what gravitational waves are and what we are actually talking about. But before that, let me just go on and say that if you are out far from the cities and you look up at the sky and you don't see, you're far from any lights and from any city, and you look up at the sky, you will see a lot of stars. You see a lot of the universe. But every star you see there, you see because it emits some light, because it's made of atoms like me and you, and those atoms emit electromagnetic radiation, which is one form of light or radio waves or something like that. So we have quite recently, maybe only 20 or so years ago, we have discovered that actually the amount of stuff in the universe that we can actually see is very, very small. So if this pi represents our universe, then about 5% of all the stuff that is in the universe is actually made of stars, atoms, and things that we can see, and we can see that because it emits light. Then it turns out that something like a quarter of the universe is made of things that are dark. We know that they are there because we really know that they have some mass and we can see the gravity, but they're dark. They don't emit any kind of light or any kind of radiation that we can detect. And so that's why we call that dark matter. And then it turns out that something like 68%, so a big fraction of the universe, more than half of it, is actually made of stuff that we, in astrophysicists, call it dark energy, which is just a way to say that we really have no idea what that is. But we know that it's dark because it doesn't make any light, and we know that it must be there, otherwise the universe wouldn't behave the way we believe. So why am I? The reason I'm telling you this is that up until 5-6 years ago, we were only able to study the universe pretty much only using light and radio waves and similar kind of radiation. So we were not able to see any of those dark things that and those unknown stuff that is there. But now, since we are able to detect the gravitational waves, those are signals coming from the universe that are emitted by anything that is out there that has some mass. And so if you remember what I just told a couple of minutes ago, those dark things here, those 27% of the universe, we know it's there because we know we need its gravity to make the universe behave the way it behaves. And so gravitational waves, as you can imagine from the name, they are related to gravity. And so we hope that we will be able, and we already know that we are able to study new objects out there that are dark, that they don't emit any kind of light, but we can see them because they emit gravitational waves. So hopefully this makes a good point, a good argument to say that it is actually interesting to try and study gravitational waves. Then, of course, now at this point, I have to explain to you what gravitational waves are. So let's just split these terms in two, and let's just start with gravity. So what is gravity? Well, so maybe you have heard of this guy called Albert Einstein. I mean, not everybody knows his name, but almost 100 years ago, a little bit more than 100 years ago, Einstein really understood how to properly describe gravity. And so before that, Newton and everybody thought that gravity was sort of a force, that everything, that Earth is pulling the moon, and so that's why the moon is moving around the Earth. Or Earth is pulling us, so that's why if we jump up, we're just coming down. But actually, Einstein explained and understood that gravity is more like a property of space itself. So imagine that the universe is like a big, sheet made of rubber. And if you put a big ball at the center, this will bend down the rubber. So it will make a sort of a hole in the rubber. And so if you have a small marble and you try to make this marble go around this rubber sheet, then what happens is that the marble doesn't go on a straight line, but it's kind of falling toward the big thing in the center. Not really because Earth or this object they put in the center is actually pulling the marble or pulling the moon, but because the moon is moving in space-time that is curved because of the presence of Earth. And so the moon thinks it's going on a straight line, but the only straight line that the moon can follow when the space is set, it's curved, is a orbit which is circular and goes around the Earth forever, or almost forever. So this is quite a big change in our understanding of gravity, because it tells you that every object that has some mass actually deform, curve space-time. Everything, including me and you, since we have mass, we deform space and time. Of course, since my mass is way, way smaller than the mass of the sun or the mass of Earth, the deformation I make is really small, so it's not really important. But of course, we have to consider what is the deformation creating space and time, but very big objects like stars, planets, and things like that. So this is how gravity works. So then gravitational waves are created, imagine where you have two objects like those two stars that are represented here, that are actually moving one around the other. And when that happens, think each of those stars will create a deformation of space and time. Since you have two, you have those two deformations. But since they're moving, the way space and time changes, those deformation is changing over time. So it's like what happens when you have something on a pond of water and it's moving, you create ripples that goes away, that propagates away. So those are gravitational waves. They are deformation of space and time itself that are created by big objects that are moving one around the other. And those are waves that propagates a wave away in the universe. It's like light or radio waves, but instead of being made of photons, if you want, they're made of oscillations of space and time itself. So they're really a complete different kind of object of radiation, of signals that come from the universe. So what kind of object can actually generate gravitational waves? Well, so in theory, everything, including me, now that I'm moving, every moving object creates a gravitational wave. But to create enough that we can actually see and detect and that they have any significant effect, you need very, very big objects. And the kind of objects we are considering are black holes. So this animation you see here shows those two black dots or spheres. Those are two black holes. So this is an actual simulation of what really happens out there. So when you have two black holes that are moving one around each other, they emit gravitational waves because they deform space and time. But like everything that emits some radiation out, they lose energy. And by losing energy, they get closer, closer, and closer until they collide with each other, until they fall one into the other. And then you see at the very last moment, they just generate those final ripple in space and time that goes away, that propagated through the universe. and then they form one single black hole. So those are some of the objects that we see out there in the universe that they collide with each other, and they can generate significant gravitational waves. So maybe the question now is, nice, but what is actually a black hole? What are black holes made of? So let's move on and let's try to explain what a black hole is. So everybody, you have tried to, toss a stone or a ball upward, and if you have a rock in your hand and you throw it upward, it will go up, up, and up, and at some point it will move slower, slower, and slower, and decelerate, and then start to come back. So if you throw something, the faster you throw this thing up, and the farther away it will go from you, from the surface of the planet. So there is a particular velocity, which is called the escape velocity, such that if you throw something fast enough, faster than that particular velocity, then this object won't fall down anymore, because it's able to go away from Earth, and the gravitational pull from Earth becomes smaller, smaller, smaller. If this object is able to go away fast enough, it will finally escape the Earth gravity. And this is how we use rockets to push things up and put them in orbit. So you can also imagine that the more mass you have in the planet, so if we have Earth and we made a lot more mass in it, then the gravitational pull will be larger. And so you would need more speed to be able to escape. And also, if you take the same amount of mass you have on Earth and you make it smaller, then you have the same amount of mass, but everything is closer to your object. And so again, the gravitational pull will be stronger. And so if you have more mass, if you have a smaller object, so the same mass compacted in a smaller object, you need more speed. So you can imagine you could take Earth and make it smaller and smaller and smaller, and the escape velocity will get larger and larger and larger. But physics tells us that there is actually a speed limit in the universe. So nothing can travel faster than what we call the speed of light, which is about 300,000 kilometers per second, which is a pretty fast speed for any kind of things we do in our real life. But this is a law of our universe, a physics law, that nothing can travel faster than that. So you can imagine then that you can take Earth and make it smaller, and the escape velocity gets bigger, and then smaller and smaller and smaller. At some point, you make it so small that the escape velocity became so large that it would need to be faster than the speed of light. But nothing can move faster than the speed of light. But this means that if you make an object small enough, nothing can escape from it, because to escape, it would have to go faster than the speed of light. What you get is a black hole. It's called a black hole because, with a little bit of lack of fantasy, if you look at it from outside, it's black because nothing, not even light, can escape. So everything that falls in just can't escape. So how big would a black hole be? Well, pretty small for all things that we consider. So if we keep doing what the experiment I was telling you earlier, so you take Earth and you make it smaller and smaller and smaller, you need to compress all of Earth to the size of about 9 millimeters, a third of an inch, something like this big. And at that point, it will become a black hole. So pretty small. Of course, if you take something like the sun, which is way, way bigger, then you have to compact it to about 3 kilometers, or a little bit less than 2 miles to make it a black hole. So this gives you an idea that objects that are of the size of stars, like the sun or bigger, if they become a black hole, and they do that when they are at the end of their life, then they are pretty small. They're, the size of a city or something like that, of a mountain. So they're really very small objects, but they curve so much space and time that nothing can escape from them. And, up until a few years ago, we had some sort of indirect proofs that there were black holes out there, but we never really understood if that was real. We never really saw a black hole, because you can imagine you can't really see the black hole because it's black. All you can see is what happens when two black holes collide, because they create gravitational waves, like I was showing a few slides ago. Or you can see if there is a lot of normal matter, like gas or stuff like that, of dust that is actually falling into the black hole, because that will become superheated and emit light. And actually, I'm sure you have seen this picture. This is actually the very first image of what a black hole looks like from far away. So this is the super big black hole, which is at the center of a galaxy that is something like this is called M87. It's many light years away from us. And what you see here is all the radio waves that are emitted by the hot gas which is falling into the black hole. And this dark side inside is what is called the event horizon. So it's that distance that separates what can escape and what cannot. So if you were sitting on that surface, then to escape the black hole, you would have to travel faster than light. So nothing, not even light, can escape from that. So that's why it's dark. So this is a quite impressive picture if you want, because it shows you exactly what a black hole is supposed to look like. And this is exactly what people were expecting. So it was quite exciting to see these photos when they actually made it available 2 or 3 years ago. So far we talked about gravity, about gravitational waves. We said that black holes are some of the objects that when they collide, they create those ripple deformation in space-time that we call gravitational waves that propagate away. So what happens when a gravitational wave actually coming from the collision of two black holes travels through most of the universe and gets here to Earth? So what happens is that they deform space and time, as I was saying. So imagine you have a ring of objects like this one in space. You're not touching them, you're not doing anything, they're free there. If nothing is happening, they would just sit there, be round and quiet, and nothing would happen. But if a gravitational wave is now coming through the screen, then this creates, as I said many times, a deformation in space and time. But what this actually means is that the distance between those objects is changing over time. So first of all, it's a wave, so it's coming and going. It's getting bigger, larger, and smaller. So that's why you see this oscillation pattern. And then the particular property of gravitational wave is that it would squeeze the direction at a given time, while the perpendicular direction gets larger. And then just a small amount of time later, the opposite happens. So the direction that was larger gets squeezed, and the direction that was originally squeezed gets larger. And so if there was a super big gravitational wave coming through the screen, what would be a perfect steel ring of object would behave like that. So you can understand that the way to detect the gravitational waves is just to monitor the distance between very, very quiet objects and see if it changes over time. Of course, if this was the effect, if gravitational waves were this big, it would be super easy. Luckily, or unluckily, depends which side you want to be, this is not the case. Luckily, I mean, because a gravitational wave this big will squeeze and ourselves too. So that would be quite annoying, let's put it that way. But luckily, the effect of gravitational waves is much, much smaller. So how small? Imagine this is a hydrogen atom. So then we zoom in and we zoom in and we keep zooming in until we get to the nucleus, which is a proton. Then we have to still zoom in, and then we are at a distance which is about a thousandth of the size of a proton. So this is how small the change in distance between object is, or how small the deformation of space and time is when it's generated by the collision of a couple of black holes somewhere out there in the universe. So this is really, really a small change. We say that it's on the order of 4 times 10 to the minus 18 meters, which is a way scientists write these small numbers, which means it's basically 0.0000. You have to put 17 zeros there and then a 4 meters. So it's really, really small. It's like measuring the distance from here to the closest star, which is Proxima Centauri, with and being able to measure a change in this distance, which is about the size of a human hair. So it's a really small variation. So you might tell me at this point, this is hopeless. There's no way we can, on Earth, build an instrument that is able to measure such a small variation of distance. Well, you would be wrong, because it took us, and by us I mean the scientific community, almost 60 years to get there. But we finally managed to build instruments that have the sensitivity to detect such small effect on Earth. And so something like about 6 years ago now, we managed for the first time to detect the first signal coming from two black holes colliding out there in the universe. And that was quite a remarkable result. And time has passed, and now we are able to detect almost one or two events like that happening out there in the universe every week. So it's quite, and it's very interesting because we have a lot of new signals that we weren't able to see before, and we are really learning a lot about our universe. So the next question, of course, would be, how are we possibly able to detect such as slow changes, slow variation? And so let me explain it a little bit, and to do that, I'll use this animation. So the way we detect gravitational waves is by using what is called a laser interferometer. It's a fancy word to say that we have a laser, which is shown like here, that generate a beam, and this beam is split into two equal parts by this mirror, this beam splitter. So the mirror travels a long distance, 4 kilometers, about 3 miles in one direction, and 4 kilometers in the orthogonal direction, and then comes back and recombines here. So what happens is that if the two distances are exactly the same, the two lasers that come back, they can interfere with each other, which means that when one wave is going up, the other is going down, and then they cancel each other. And so you don't see any light there. But then remember that if a gravitational wave is coming through, it will change in a different way the distances of objects in the two perpendicular directions. And this means that one of the two arms of the interferometer, one of the two directions, will get a little bit longer, and one will get a little bit shorter. And this means that the laser beam that travels in one direction will get back a little bit delayed because it has to travel a longer distance. And the other beam will come back a little bit earlier because it has to travel a shorter distance. And so the two waves that were canceling each other perfectly at the beginning, they don't cancel each other anymore perfectly. And so you get some light coming out on your detector there. And this is exactly what is happening here. You go from perfect cancellation on the two waves, then the gravitational wave is coming by, and that perfect cancellation doesn't happen anymore, and then you have some lights. So this is how our instrument works. When a gravitational wave comes by, it changes the length of the two arms, which are 4 kilometers long, by a very, very small amount, thousands of the size of a nucleus of an atom. But that's enough to actually perturb this perfect cancellation and create some light that then we can detect. And that's how we detect gravitational waves. So this is how the two LIGO instruments work. So let me now move on and show you actually real footage. So this is an aerial image of the detector that is in Washington State, what we call the Hanford detector. And you saw that building in the central area is where the laser is generated. This is the other detector that is instead in Louisiana. So that big building is where the laser is generated. Then you see the two arms. One is pointing in one direction and one is pointing in the other direction. So the laser travels 4 kilometers inside a vacuum tube to go to the end mirror. So this is, of course, an animation. These are not real images, but we will soon see some real images. Because then the laser has to get to the end, and you see some of the actual equipment that we have in our detector. And so then the two lasers comes back, they recombine again in that building, and then we can see if we detect a gravitational wave. You might wonder why we have two instruments like that. So one in Washington State on the West Coast and one in the South in Louisiana. The reason is that we need to have two detectors far away. So when a gravitational wave comes by, depending on where it is coming in the sky, like it's represented in this animation here, it would first hit one detector and then hit the other one, because gravitational waves also travel at the speed of light. So the distance between the two detectors is about 3,000 kilometers, which means that gravitational waves will take about 10 thousandths of a second, 10 milliseconds to go from one detector to the other. And so by measuring the time distance, the time difference between when the wave arrived to one detector and then to the other, we can actually do something which is called triangulation, which, if you want, is very similar to what our brain does when we listen to some noise. If even if you close your eye and you don't see anything and you listen to my voice, your brain is able to guess from which direction the sound is coming. And the way that works is that because it's working because we have two ears, and then if the sounds come to one ear a little bit earlier than the other one, then the brain is able to tell us that the sound is coming from a direction which is closer to one ear than the other. And we do exactly the same thing here with the gravitational waves. That's the reason to have two or possibly more detectors in the future. So I just want to give you a brief idea before we close up of the kind of technology that is needed to make such a discovery possible, because I showed you a very simplified scheme of how a laser interferometer works, but you can imagine that to be able to go to those very, very small changes in distance, we need to have very precise measurements. So for example, I briefly mentioned already that all our system needs to be in vacuum, meaning that we need to have some big containers, if you want, and we have to pump all the air out of it, because otherwise all the fluctuation in the air would give us a spurious signal, which would be way, way larger than anything we can actually record from a gravitational wave. So we have to get all the air out, otherwise that would be overwhelming over all our signals. Then the mirrors that we have to use, and you can see here where it says core optics, and you probably can see my pointer, those are two of our mirrors. So they look a little bit different from what you imagine as the mirror you have in your bathroom or at home. And the reason is that we need them to be very high quality. The mirrors we are used to have in our bathrooms, in our houses, they maybe reflect 90% of the light that goes into them. And that's fine. It's not fine for us. We need to be able to reflect more than 99.999%, because if we lose even a little bit of light, then that will be again a problem, because that will limit how sensitive we are in our ability to detect the gravitational waves. But then, even when there isn't any earthquake or there isn't any big disturbance, the ground is always shaking a little bit, because there's a sum of all the human activity and people shaking the ground all around, and earthquakes happening all around the world. So the earth is always shaking millions and millions of times more than the effects that we actually want to detect. And that's why our mirrors, they cannot really just sit there on the ground, but they have to be suspended to very complicated systems that are able to isolate them from the motion of the ground. So this is just a few examples of all the technology that we had to develop over years and years to be able to get to this sensitivity. So that's also why it took a long time to build and make those instruments to work. So what are the results at the end of the day? So this animation here shows you, and I'm going to stop it at the beginning. So up to maybe 6 years ago, this was all that astronomers knew about neutron stars that are very compact stars that will reach the end of their life. They become very, very compact, but they're not big enough actually to collapse to the point that they're small enough to create a black holes. So we see a lot of them. We see some of them are represented here. And the number you see tells you how big those objects are. So 1 means that they're as big as our sun. 2 means that they're twice as big as our sun. And so you see that neutron stars, they can get only as big as twice the sun. If they're bigger, then there's so much mass that they cannot really stand the gravitational collapse anymore, and they become black holes. And so there were a few evidence of black holes that were seen by the fact that people actually saw stuff falling in. You can't actually see the black hole, but you see something that is moving around and then disappears, and for seeing like gas or dust and stuff like that. Then we started detecting gravitational waves. And so we started seeing a few objects and then more and more and more. And this is the situation right now. So we went from just knowing that there were a few objects there that we believed were black holes to actually seeing a lot more of black holes and even much bigger black holes that were colliding and creating a new one. That's why you see always two dots here that then they're joined by an arrow and they all go to a bigger black hole. So you see, this means that those two black holes were the two original objects that were moving one around the other, and then they collapsed, they created one other object out there. So just to give an idea, before the discovery of the first discovery of gravitational waves from two colliding black holes, astronomers didn't really believe that it was possible to see black holes like that. They didn't believe that there were a lot of black holes that were orbiting one around each other, close enough that they could actually fall into each other. And that was kind of a surprise. But a good surprise, because this is how science works. You build an instrument to try to expand your horizon to see more, and often nature doesn't give you exactly what you were expecting, but gives you something new. So what we were expecting were the few events that you see down here. So two neutron stars colliding and creating another object, probably a black hole or another neutron stars. Since we knew there were a lot of neutron stars, we knew that that would have eventually happened. But seeing so many black holes was a surprise. And so this forced us to really change our understanding of the universe. So far, the LIGO detectors, so the gravitational wave detectors that we have all around the world, they've been operating for the last 5 years, not all the time, because we like to make the instrument work and improve it as much as we can, then just pause and let it go and listen to the universe and see what signals we get. And then after a while, we say, okay, now we know how to improve even further. So we stop, we do some more work on our instrument to make it even better and better and better. And this is how where we are right now. After the last observation period, so we call them O, O1, O2, O3, those are the observation times. So the last one, O3, was almost a year long and ended in the beginning of 2020. And so after that, we are now working to further improve our instrument. And we expect to be back sometimes in summer of next year with a much improved instrument. So being able to detect even more signals. So we know that we will see more gravitational waves coming from neutron stars, more gravitational waves coming from black holes, and who knows what else is out there. So that's always the fun part of this job, that you never know what to expect. With that, I think I chatted long enough. So I want to leave you with this last slide where you can find a lot of references. So you can go to this website, ligo.org, and from there you can actually access a lot of very good information. And we have some videos that tells you the story of our detectors, the story of gravitational waves, and will explain you even more and more details. And of course, you can always follow us on Facebook and Twitter. We have accounts and we post when there are new discoveries. Or you can just contact me at the email below, and I'll be happy to answer any question, of course, that you have. With that, I want to thank you for your attention and open the floor to you for questions, comments, or anything you might want to ask.
I have a question. Are gravitational waves, do they go in a certain direction, or am I asking the right question? I'm not really sure. Are they like motion? Are they a certain pattern?
Mm-hmm. So that's a great question, and I kind of didn't cover that much. So luckily for us, when two objects like the black hole that was showing collide, the gravitational waves that are emitted, they move pretty much in every direction, which is good for us, because it means that we don't need to be lucky and to have like the headlights of a car pointing directly at us when the gravitational waves are emitted, because they go in all the direction in the universe. And so it's we can basically see any collision of object of any source of gravitational waves anywhere in the universe, regardless of how they are oriented, because the signal goes out in all directions. So this is good, but it's also bad, if you want, because it means that all the energy that is emitted in the collision of the two black holes, for example, is actually spread over the whole universe, if you want. So when the gravitational wave signal propagates away, the energy spreads over a bigger and bigger and bigger surface. So that's why when the two black holes collide, the amount of energy that is generated is incredible. It's like converting 3 times the mass of our sun into pure energy. But then by the time those gravitational waves have traveled through something like 1 billion light years in the universe and they get to Earth, they spread out so much in this big surface through all the volume of this universe that basically the effect that we see is really small. That's why it's so hard to detect them.
That was going to lead me into my next question as far as how far they travel and what's the which one have you detected any that have traveled a very, very long distance?
So the gravitational waves can travel through the universe and through matter and space without being much affected, meaning that they can travel through the whole universe, which is a long, long way to go. So the how far we can detect the gravitational waves now is not really limited by how many binary black holes or sources there are out there, but it's limited by how sensitive our instrument is. And that sort of makes sense. Think of our instrument like a microphone, right? The microphone has just some sensitivity. If I'm talking to the microphone, if now I started walking away from the microphone, at some point you don't hear me anymore because my voice become, so low in volume that is covered with anything else, or the noise on the microphone, the noise in your room, and all of that. So the farther away the object is, and the fainter it is, so the harder it is to actually detect. So the sensitivity of our detector, how good we were in building good instruments, this is what actually limited how far we can go. So we have detected the signals, gravitational waves coming from colliding black holes as far as a few billion light years, maybe 10 or 20 billion light years. So it means that those signals, those two objects actually collided something like billions of years ago. And then the signal traveled through a big chunk of the universe and got here after traveling for billion of years. Because it's always confusing when you say the distance in light years and then you use the same number as the time it takes for the signal to get here. But that's exactly the idea, because 1 light year is how far light can travel in a year. In gravitational waves also travel at the speed of light. So saying that we detected the two black holes collided at a distance of 10 billion light years, it means that they actually collided 10 billion years ago. And that gives pretty much the idea of how far those objects are. So they're not part of our galaxy, they're part of other galaxies that are very far from us.
Any more questions?
So is it theoretically possible that 2 black holes that have merged into one, so that black hole merges into another one? And then have you guys ever recorded any data that might point to it? Yeah,
no, that's a good question. So what we are able to detect is exactly what you were mentioning. So it's exactly 2 black holes like the 2 that I'm showing here. So those are the 2 dots are 2 separate black holes that they get close to each other, so they start moving one around the other, and then eventually they fall into each other, and so they create one bigger black hole. So this is all This is actually the kind of gravitational wave signals we see. And we can actually, from the shape and the properties of the gravitational waves, we can tell how big the two black holes were and how big the final black hole also is.
What is your favorite part so far about your job, and what is the most interesting thing you've discovered or learned in your job?
That's a great question. So what I do as a member of the LIGO collaboration is actually to design and build those instruments. So I'm what is called an instrumental scientist. So my job is actually to look at the current instruments and try to figure out how we can make them better in the future. So that's a very, for me, it's a very interesting job, because you are essentially, every morning you wake up and you know that you have to solve a problem that nobody has solved before, because you're just pushing a little bit farther the limit of how good an instrument you can build. So that's a very, from an intellectual point of view, it's very stimulating. It's always fun when you know that whatever you discover is going to be something new that nobody was able to do that before. And then what I really like is that to be able to do this, we really need to put together knowledge for a lot of different fields. So it's not that I'm always focusing on a very narrow topic, but I have to learn a little bit of a lot of things. So I had to learn how to work with laser systems, how to work with optics and lenses and mirrors. But then I have to learn a little bit of chemistry and material science, because you have to actually build those mirrors. So to build those mirrors, you have to find the right materials. And so it's always, what I like about my job is that it's always about learning something new. You never get bored here. You never stop learning. It's not that you go to school and you get your degrees and then you don't need to learn anything new. Actually, when you get your degree in physics or your PhD in physics, that's what you get to when it's like a doctoral research level. What you actually learn is how to learn. So you learn to be curious and how to attack a problem and learn the new things that you don't know to try to solve that problem.
What's been your favorite project so far?
So actually, the most interesting thing that I have worked so far on a really practical project, which is I'm still working right now, is to find and develop new materials to actually make those mirrors. So the example I was giving you earlier was not just made up. It's actually one of the main things that I'm doing right now. So if we go back to one of the pictures of the mirrors here, you see that they are big pieces of glass. But glass, of course, is transparent, right? So to turn a piece of glass into a mirror, you have to put something on the top that actually make it reflective. And it turns out that it's really hard to make mirrors as good as we need. And so even though we have now mirrors that are pretty good, actually the properties of that very thin layer of materials that you put on top of the glass to make them reflective is what is right now currently limiting how sensitive our detectors are. So which means that the physics of what happens in this very, very thin layer of stuff you put on the mirror is actually limiting how good you are to reach out in the universe. And so what I'm working on right now is to find ways to improve the properties of that thin layer, so to improve the mirrors. And that's something that I found very interesting. And I also find fascinating the fact that to be able to learn more about the physics of black holes and what happens far out there in the universe, we actually need to learn the physics of atoms and stuff that are on a very, very small scale. It's like you are really linking what happens on a very, very macroscopic scale to what you need to do to be able to study the very, really big macroscopic scale.
So we were talking about you were talking about black holes, right? So are they the only uh, are are black holes the only ones that emit gravitational waves, or does Earth, for instance?
So every object that has some mass and it's moving and it's accelerating emits gravitational waves, which means that now when I'm doing this, I'm moving, I am also emitting gravitational waves. The problem here is the scale. My mass is not as big as the mass of Earth, of the sun. So the amount of gravitational waves that I'm generating is so incredibly small that it's basically impossible to detect them. Even Earth moving around the sun emits gravitational waves. But still, even at that scale, the amount of gravitational waves that is emitted is very, very small. The amount of power that is emitted by the Earth going around the sun in terms of gravitational waves is of the order of 200 watts. So it's pretty much as much energy as you need to power a light bulb. But that's, spread over the whole size of the Earth orbit. So it's already very, very small. So you really need to go to big astronomical objects to create a significant amount in gravitational waves. You need big objects and objects that move fast. So that's why, two black holes that collide, or two stars that at the end of the life, they're moving closer and closer to each other and they collide. Those are possible sources of gravitational waves. So these are all what we call, this is a particular category, a particular class of objects, which are when you have two binary systems of two objects that are moving around each other, and then they fall into each other, and then they generate gravitational waves when they collide. And they can be black holes, they can be neutron stars, they can be a neutron star falling into a black hole. So those are the things that we have seen so far. We expect other sources out there. For example, you probably all know that stars, when they get to the end of their life, they go through a phase which is called a supernova. They explode because they don't have enough nuclear fuel anymore in their center. And so there's nothing that prevents the star from collapsing. And when the star collapses, all the external part of the star just fall into the nucleus of the star and it bounces off, and that creates a gigantic explosion, which is a supernova. We also expect that gravitational waves are generating this big explosion. We just were not able yet to detect them because, first of all, we are not quite sure how much energy will be emitting gravitational waves. And then also we are not quite sure what is the kind of shape of the waves that are emitted. But we're still looking for that. So that's another example of sources of gravitational waves. Then, of course, you can imagine that the biggest explosion of all of them was the Big Bang. So at the beginning of the universe, this big explosion has also very likely generated gravitational waves, but we believe that they are very, very weak. So we are not sensitive enough to see them. But hopefully in 10 or 20 years from now, our instrument would have got better and better, and then maybe we'll be able to do that too.
Perfect. We have a question in the chat from Sanjay. What are the biggest limiting factors for more precise detections of black holes and neutron stars?
That's a great question. So the sensitivity, so how far, how precise we can detect those signals depend on how sensitive our instruments are. And so how small is the change in that distance that we can measure? Because if we could measure 10 times smaller distance change, then that will make us 10 times more sensitive, meaning that we can detect the same kind of collision 10 times farther away in the universe, or the same 10 times better. So there's a lot of different disturbances that limits our sensitivity. Imagine like you are in a room full of people and you're trying to listen to the voice of a very specific people while there is a lot of background noise. So that background noise is what is actually limiting our sensitivity. And right now, there are two things that actually are limiting how sensitive we are. The first one is due to the properties of the mirrors, what I was mentioning earlier. So you all know that probably that every single atom vibrates a little bit because of a thermal motion, because what is called Brownian motion. So all atoms in all objects, they jiggle around a little bit. This is very, very small, but we are also trying to detect an extremely small effect. So the motion of the atoms on the surface of our mirrors is what is actually right now limiting how sensitive we are. And this is part of the job that my main responsibility, which is to try and find ways to make those atoms move less. That's one of the contributions to what limits our sensitivity. The other is actually the fact that we're using lasers to measure the distance. And lasers are made of photons. So they are, you can imagine that a powerful laser beam is made of a big amount of a large amount of photons. But then, of course, there can be a little bit more, a little bit less photons. The amount of photons your laser beam isn't constant over time. It kind of fluctuates. And it fluctuates because of the intrinsic, if you want, quantum properties of the laser. So what is called the Eisenberg uncertainty principle, if you haven't heard of that, it tells you that you can never measure something with absolute small precision. There's always some fluctuation due to the quantum randomness that is intrinsic in everything. So this is the other thing that is actually limiting the sensitivity right now. And that's why we, from time to time, we stop taking data and we try to improve the detectors, for example, with better mirrors or with more powerful and more precise lasers. And that's how we keep pushing the sensitivity down and down, and so making the instruments better and better.
So you mentioned energy and the amount of energy that's emitted, which is like you said, enough to light a light bulb, right? So
Maybe we lost you. I don't know if I'm the only one not hearing her anymore.
okay, I think we're back.
We can
Okay,
hear you now.
I can hear you now.
Yeah, so what was your question? I lost you when you said
About energy, harnessing the energy from gravitational waves. Is there a way that they try to harness that?
so no, because the amount of energy, so if you were right where the two black holes collide, the amount of energy emitted is incredibly high. But they are so far away that by the time the energy comes, the gravitational waves come here, the actual amount of energy we detect is extremely low. I was just mentioning that the Earth moving around the sun emits enough energy in gravitational waves that would be enough to light a light bulb if we were able to collect all of that. But if you have two black holes that are, 1 billion light years away in the universe, by the time the energy comes here, since it's spread everywhere, the amount is so small that it's basically zero. There's a very, very small amount of energy, so it wouldn't make any sense to try to collect that energy. This is also why it's so hard to detect gravitational waves, because by the time the signal goes here, it carries very, very small energy.
Oh, so by the time it gets here, it sort of dissipates. Does it go away altogether, or is it like a loop?
So you have to think that the amount of energy, so if you're very, very close to the black hole, the two black holes colliding, they emit an incredible amount of energy, like 3-4 times the mass of our sun just going into energy. It's more energy that the rest of the universe emits in light in the same amount of time. But then that energy is going in all directions. So when it gets farther away, it's spread over a larger surface. Then if you get 10 times away, 10 times farther away, the same energy is spread over a surface which is 100 times bigger. and so far and so far and so far. So the energy isn't dissipated, you just spread it out to a bigger and bigger and bigger surface. So by the time you get here, all that energy that was emitted right where the two things collided is spread over a surface, which is a sphere with a radius of about 1 billion light years. So it's a huge sphere. So the amount of energy that I can actually capture because it's close where we are is extremely small. The total energy is still huge, but the amount that comes in our direction is very, very small.
Oh, thank you. Okay, one more question from the chat. What are the biggest limiting factors for more precise directions of black holes? Oh, wait a minute, sorry. I asked that one. Do all objects in space produce gravitational waves? For example, the sun and other stars.
Yes, so all objects that move and accelerate in the universe, they produce gravitational waves. So the sun going, the Earth going around the sun, or even the moon going around Earth, or even me moving right now, I am emitting gravitational waves. The problem is that the amount of energy that I'm producing is incredibly small because my mass isn't that big. So even though everything in the universe produces gravitational waves, only very, very big objects produce strong enough gravitational waves so that by the time they get here, we can actually see them.
These are so good. All these questions are great. We have a few more minutes. If anybody has any more questions, Gabriele can answer them. How can they reach you if they have questions afterwards?
Yes, so the best way to reach me is to send me an email at the address that is written down here at the bottom of the last slide. So that's the easiest way to reach me out. Or you can always go to the LIGO.org website, and there's a lot of information there and a lot of videos that we made, and people that are way better than me at explaining things. They took their shot at explaining a lot of the complicated things that we do. So take a look at that, and you're free to contact me if you want.
Perfect. Somebody else asked a question real quick. Let me grab it. So would the noise in your data be the gravitational waves produced by other objects in space like stars?
I'm not sure I understand what the question.
Yeah, so so when you're detecting the gravitational waves from black holes, for example, how would you know that is indeed from a black hole and not from like a lot of other stars combined, like the gravitational waves from a lot of other stars combined?
Oh, that's a great question. Thank you. So when we detect a gravitational wave, we can see what is the shape of the wave. And actually, in this last slide, you can see this image here shows you all those wiggles there. It's actually a real measurement of the first gravitational wave signal we detected. So as time moves on, the distance between the mirrors and our detectors moved stronger, stronger, and stronger, and then they didn't move anymore because the two black holes had collided. So if you look at the shape of this signal, you can actually understand what the source is. It's like saying that if you are listening to a sound, you can tell from the sound what musical instrument is playing, right? Because the property of the musical instrument are somehow encoded in the sound. So you can tell the difference between a string instrument or a percussion or anything like that, not because you see it, but because you can actually look at the properties of the sound. And we do the similar thing. So by looking at the properties of the gravitational wave signal that we see, we can actually compare them with what we expect from black holes colliding. And so we can actually tell, yes, this is a gravitational wave coming from through two black holes, or from two neutron stars, or from a neutron star falling into a black hole. In the same way, we can also tell apart real signals coming from gravitational waves coming from the universe from local disturbances that would have no reasonable shape.
Thank you.
Thank you for that question. All right. That should do it. We're at 5:30. And I really appreciate all of you guys for tuning in, especially the ones here. We know that it's a holiday weekend and a lot of people try to disappear, but we really appreciate your support. I really appreciate you, Gabriele, for coming in and speaking to the students and the people that I invite from Eventbrite. We love to see you again. We always like to put you guys on rotation. So I hope you'll be available in about 4 or 5 months. We'll get to you again by then. And I really thought this was an awesome presentation. And I'd love to hear more. I could ask questions all day, but we don't have all day. But if anybody else has a question before we leave, I think I saw one. Hold on. Oh, somebody said thank you. Have a great weekend. Thank you.
Well, thank you for inviting me. It was a pleasure, and I'm always happy to come back anytime.
Oh, great. And if you guys have a question, if he's too busy to get to you, just the email that we sent you the invitation with, go ahead and email us, and then I'll ask the question also. I could get to him also. But I really appreciate your time. And then we'll see you on the next one, okay?
Sounds great. Have a nice weekend, everybody.
All right. Thank you, guys.
All right, thank you.